Let f of x equal y, which is the cube root of 3x. Now, the funny notation there is really just emphasizing that f of x defines the variable y and is equal to this function. So just for emphasis, I'll explain in a bit why I've done that. Consider the portion of the curve where y is between 0 and 2. Find the surface area of the surface generated by revolving the graph of f of x around the y-axis. Okay, so first let's take a look at our graph. So this is essentially a cube root function, and cube root functions have a similar look to square roots. It's just that they kind of go off in both directions. But we're only interested between where y is from 0 to 2. So that's going to be from y equals 0 up to, say, y equals 2. I'll just put that there. All right, and we want the arc between there. So this arc right here is going to be rotated around the y-axis. So we're going to rotate around this axis here. So that's going to produce a surface of revolution, this hollow object that we want to find the surface area of. Okay, formulas for surface area. We have effectively two, and I'm going to show you both here. So 2 pi times the integral from a to b. Actually, let me be a little bit more careful there. I'll say this is c to d so it doesn't get mixed up with the others that I have, of g of y times the square root of 1 plus g prime of y quantity squared dy. And this is the surface area formula when we rotate around the y-axis. Now, another form here is 2 pi times the integral from a to b of just x times the square root of 1 plus f prime of x squared dx. I'm going to show you how both of these work here. First off, let's take a look at our function. So this is the function we were told is f of x, and that is the cube root of 3x. Now, we know that f of x is interchangeable with the variable y, but I want you to see what this g of y function is. So if I were to solve this in terms of the variable, get y, or x by itself, and write in terms of y. So this would be y cubed equals 3x, or x equals 1/3 y cubed. Then I could equivalently say that this is g of y equals 1/3 y cubed. All right, and that being the case, I can actually use this first method here. Let's say this is a. And if I am solving using that formula, I can say my surface area is 2 pi times the integral, this is on the y-axis now, so from 0 to 2, g of y, so that's 1/3 y cubed, times the square root of 1 plus g prime of y, so probably need to go off to the side to get that, so g prime of y, we have 1/3, bring the 3 down, and subtract 1 from the exponent, so the third and the 3 cancel, so that's just y squared. So this becomes y squared quantity squared dy, or fairly simply here I could say this is 2 pi over 3 times the integral from 0 to 2 of y cubed square root of 1 plus y to the 4th dy. And this is something I could very much just toss right into fnint, get an actual answer here. I'm going to approximate it to 3 decimals, although I could could probably use u substitution here because the part underneath the square root is power of 4. The part on the outside of the square root is a power of 3, which is 1 less, so I think I could use u substitution pretty easily, but we'll just continue using fn ent for any of these approximation ones. That's fine. So, oops, math 9 going from 0 to 2, and this is y cubed times the square root 1 plus y to the 4th dy. Alright, of course I'm just substituting x's, which is fine in this case. So that's what I get, and then I would need to multiply that by 2 pi over 3. So 24.12, we'll just say. So this is approximately 24.12. Okay, now let's do this again in a different way. All right, using the second formula. So using the second formula, everything is in terms of f of x, which is just the same function but solved for in terms of x. So you have y by itself and in terms of x, so written as is, basically. I again will need a derivative of that, but well, I guess I could just go ahead and get that now. So let's see, if f of x is 3x to the 1/3 power, which is equivalent to the cube root, then the derivative of f, we bring the 1/3 down, 3x to the negative 2/3 power, and I actually need to use the chain rule here, so multiply by the derivative of the inside part, which would just be 3, so 3 times 1/3, we get 3x to the negative 2/3 power, and I think I'll just leave it like that. I think that'll be fine. Okay, so my surface area then can be written as, following this formula b here, 2 pi times the integral from a to b. So it's not c to d, it's different endpoints here because this variable is of x now, so I need to know where I'm going on the x-axis. So for instance, like this point right here is very clearly at 0, 0, and that's pretty easy to tell because if I have a y value of 0, if I plug 0 into my function g, then the output is an x value, so 0 cubed divided by 3 is still 0. All right, but over here it's not quite so clear. If I put 2 in, it would be 1/3 of 2 cubed, which would be 8/3. So the x value there would be 8/3. So I would need to integrate on the x from 0 to 8/3. And then here's something that's interesting. So this right here, this part out here, is no longer a function. It's just the variable x. So how do we get away with going from a function just to the variable x? Well, the reason it works is really very simply because the function g of y outputs the x value, and so we're really just replacing g of y with x. It's really just as simple as that. So with that knowledge, we can change g of y into x, but we need to make sure we write our function on the inside of the integral, or inside of the square root, as a function f of x equals y. So I can just make this x and times the square root of 1 plus f prime of x squared. So f prime of x was 3x to the negative 2/3, and then that's going to get squared. Then we will integrate with dx here. So if I set that up, I'm just trying to simplify here a bit. So if you take something from an exponent to another exponent, so you're raising one exponent to another, you can simplify that by multiplying. So this would be 1 plus 3x raised to the negative 4/3 dx. Now, if we tried to integrate this by hand, we'd be in a bit of trouble because this negative 4/3 power is going to make it difficult to actually perform that integration. But if we're using fnint, it's doing approximation methods anyway, so it wouldn't make any difference. We should ultimately get the same answer, and I've got my fingers crossed here. We'll see what happens. So x times the square root of 1 plus, then in parentheses, 3x raised to the negative 4/3 power dx. Make sure I've got that all in correctly, and that, we multiply that by 2 pi. There we go, 24.12 again. So we result in the same value. So that gives you a choice as to which way you want to set this up, and which is easier. Well, it just kind of depends on the functions. I think in this case it was probably easier the first way, integrating dy. And certainly if we were going to integrate by hand, we would definitely want to integrate this dy. If we were integrating, but since we were using fnint, it doesn't really matter which variable. We got the same answer both ways, so I'm not sure that it makes a difference here. And so it's really just kind of a matter of preference. But you have a choice here, and I just wanted to make sure that was available to you. All right, that's everything for this lesson.